Good afternoon everyone. Today I am going to discuss about the computer organization subject unit 3. Coming to the topic, computer arithmetic introduction. So this is the introduction of computer arithmetic. So this is the part 2 in the unit 3. Part 1 we have discussed in the previous video, that is control memory, address sequencing, micro program example, design of control unit. So these are the first part of the unit 3, and second part is the computer arithmetic. So coming to the introduction, so data is manipulated by using the arithmetic instructions in digital computers. If you use the digital computers, we are going to manipulate. In our digital computers we are having so many instructions about arithmetic instructions. So we are performing our data whatever the user need. So whatever the user need in that form of instructions we are following in the digital computers. So data is manipulated, whatever the data we are giving, like addition, subtraction, multiplication, division, anything, whatever the calculations you want, that can be provided by the digital computer, because in this we are having some arithmetic instructions. So data is manipulated to produce the results necessary to give solutions for computation problems. So if you have any computational problems, so that will be produces the result in your assumption. Okay, so data is manipulated, okay, to produce results necessary to give the solutions for computational problems. So computational problems means sometimes small equations will be solved by the user. So but a complexity of the problems not solved by the user. So the computational this computer will be, digital computers will be solve the problems it gives the solution. So whatever you need, okay, so that will be the whatever the data you have given in the digital system computer, the data is taken and it will be manipulated and produce the result. Okay, so like addition, subtraction, multiplication, division are the four basic arithmetic operations. These are the four basic arithmetic operations which is performed in the digital computers. So if we want then we can drive other operations by using these four operations. So what we are saying that, so whenever if we want we can drive other operations by using these four operations. So whatever the operations we are having in the digital computer, so this can be perform other operations also. Okay, to execute the arithmetic operations there is a separate section called arithmetic processing unit in central processing unit. So in order to execute arithmetic operation there is a separate section called arithmetic processing. So arithmetic operations in order we are performing some arithmetic operations in the digital computer that have a separate section called arithmetic processing unit. So APU, okay, arithmetic processing unit in central processing unit. So in the central processing unit what we are having a separate section is there. That section is called arithmetic processing unit. Okay, now this is the processing unit which performs the and executes the arithmetic operations. So in these arithmetic instructions are performed generally on binary and decimal data. So whatever the arithmetic instruction will be taken, that can be performed in binary. Binary means zeros or ones. Decimal data means it will be take the points like 256.5, this like decimal data. Okay, na? So whatever the arithmetic instructions are performed generally in binary or decimal data. So fixed point numbers are used to represent integers or fractions. So integers or fractions we can be signed or unsigned negative numbers. So fixed point numbers means we have a fixed point. So on that fixed number we are providing the point are used to represent the integers or fractions. We can signed or unsigned the negative numbers. So fixed point addition is a simplest arithmetic operation. Fixed point addition is the simplest arithmetic operations. Okay, so if we want to, so if we want to solve the problem, then we use a sequence of well-defined steps. If you want to solve any problem, we are following some sequence of well-defined steps. So these steps are collectively called arithmetic, these algorithms. So so if you want to perform any operations according addition, subtraction, multiplication, division, so whatever the operation you want to perform, you have to follow some rules, steps that is called algorithm. So if you want to solve a problem, we use a sequence of well defined steps. These steps are collectively called algorithm. To solve the various problems, we give the algorithm. If in order to solve the various problems, we provided the algorithm. Okay, in order to these instructions perform a great activity in processing unit, processing data in digital computer. So instructions perform a great activity in processing the data in digital computer. So what is mean that instructions means arithmetic, whatever the instructions we having, okay, arithmetic instructions, okay, that can be perform a great activity in processing the data in digital computer. Okay, so we already stated that with 4 basic arithmetic operations, that is addition, subtraction, multiplication and division, it is possible to drive other arithmetic operations and solve the scientific problems by means of numerical analysis methods. So not only we have these small additions, subtractions, multiplications, divisions. These are the simplest operations which is performed by the arithmetic operations. Okay, so I am talking about the scientific problems. If we have any scientific problems or means of numerical analysis methods, in order to solve that problems, we are using some arithmetic operations. So these arithmetic operations are used in the scientific problems and that is called numerical analysis methods. There are three ways of representing the negative fixed point. A process of a processor has an arithmetic processor such as that executes the arithmetic operations. The data types assumed to reside in processor registers during the execution of arithmetic instructions. So negative numbers. So the negative numbers may be signed magnitude or signed complement representation. So there are 3 ways for representing the negative fixed point. That is binary numbers signed magnitude and signed 1's complement or signed 2's complement. So most computer uses the signed magnitude representation for the mantissa. Okay, so this is the introduction of the computer arithmetic. So next coming to addition and subtraction. So what is mean by addition and subtraction? Addition and subtractions with signed magnitude data. So in this we are using what the main thing using by the most computer is mainly uses the signed magnitude. Okay, data, signed magnitude data is utilized. So 1's and 2's complement will be also used, but not it will be used rarely. Okay, so we designate the magnitude of 2 numbers. So A and B, I am taking the 2 magnitude numbers, that is A and B, where the sign numbers are added. So A and B, where sign numbers are added or subtracted. So whatever the 2 signs we are taking, addition and subtraction, and we are adding the 2 values and we are subtracting the 2 values, where the sign numbers are added and subtracted. We find that there are 8 different conditions to consider. So we having 8 different conditions we can be followed. Okay, now depending on the sign of numbers and operations performed. Okay, so these conditions are listed in the first column, that is table. So this is the table. So this is the number of operations we are only using the addition and subtraction symbols. Only using the addition and subtraction, we are finding the 8 different conditions that depending on the sign of the numbers and operations will be depending on the sign, the operations will be performed. So these conditions are listed in the first column of the table, and the other column in the table shown the actual operations to be performed with the magnitude of numbers. The last column is needed to present a negative 0. In other words, when 2 equal numbers are subtracted, the result should be positive 0, not negative 0. Okay, so if you see the table, you can understand. This is the sign magnitude addition and subtraction table. So addition, in addition I am using the plus. Okay, plus a plus b is equal a plus b, I am doing the addition. Okay, a is the adjoint, okay, adjoint, and b is the addend. Okay, so a minus b, this is the minend. Okay, this is the subtractand. Okay, so this is the two values I am taking. Okay, so for these two addition two symbols, addition and subtraction, we having completely 8 possibilities. So series, this is 1 2 3 4 5 6 7 8, 8 possibilities we are having. In this first table of the first column, this is the operations. First we are providing the plus, again I am providing the plus and plus b. So first operation a, I am taking the a, so before the a I am providing the plus, middle of the a and b I am providing the plus, and before the b, in front of the b also I am providing the plus. So this is called the plus of a plus b, add magnitude. So after adding, I am providing the common, this plus will be providing the common to both a plus b. Okay, and this is the when grade a greater than b, when a less than b, when a equal to b. So whenever the values we are taking, we are differentiate for that. Okay, this is the subtract magnitude. So if a greater than b, a less than b, a equal to b, this is the values. Okay, so this is the another way, another operation. This okay na? So plus a plus minus b. Okay, so this we doesn't have any add magnitude, so it will be here we are taken plus plus, so plus or minus it will be, so plus of a minus b, and here which is which value, if it is a is greater, so a minus b, if b is greater, b minus a we will take, both are equal, I will take commonly a minus b. Okay, so this like. So next this is the another operation, minus plus plus. Okay, we will get minus plus plus means minus, plus plus we will get. Okay, plus plus means a minus of a minus b plus b minus a and a minus b. This is the another operation. So this slide we having the 8 possibilities of operations in addition and subtraction. So hardware implementations, in this we having the hardware implementations. Here we having b register, complementer, parallel adder, and a register. Okay, a register, b register. In between that we are having complementer, parallel adder. So here we are load sum. Okay, load sum. Here a2, this is the b2. Okay, so what we are performing, output carry, input carry. So mode control. So input carry will be taken with the parallel adder, and parallel adder will be passes to the a register. Okay, and here the data load sum will be occurred. Okay, after that it will be given to the e. Okay, e. Okay, this is the output carry. Okay, input carry, output carry. So this is the hardware implementation. So b register will be complementer here, so it will be given to parallel adder, and after that it will be given to it will be load at the sum a register. Okay, and it will be taken by the output, e will be taken the output. So this is the working of this hardware implementation. So next coming to signed, this is the sign magnitude addition and subtraction. So now I am talking about the signed one's complement, sign two's complement addition and subtraction, sign two's complement addition and subtraction. So okay, so in this what the working, how it works. Okay, so this is the two's this is the sign two's complement addition and subtraction. So overflow, v is the overflow, and hardware, this is b register, accumulator AC, and complementer and parallel adder. So this is the algorithm. Subtraction, this is the subtract algorithm, this is the addition algorithm. So we have seen here ACB. Okay, ACB, A means already we told that this is the minute and subtractand. Okay, and this is the here in the subtraction. In the addition, it will be a adjoint and addend. Okay, so what we are taking AC implies AC plus B plus 1. Okay, AC plus it to complement this one. So AC plus B plus 1. So if you overflow, data will be overflow, after that it will be end. So this is the same as this one. So in this we are additional operation. This is the subtraction, and so this is the subtract. Okay, this is the addition. Okay, so if we are providing the plus here. Okay, this is the addition algorithm. So I having the explanation about this algorithm. So this is the algorithm. In this flow chart, the two signs A and B are compared by an exclusive OR. Okay, so here we having two signs, that is A and B. So in this flow chart, what we are having A and B with exclusive OR gate, compared by the exclusive OR gate. So if the output of gate is 0, if the output of the gate is 0, the sign are identical. If the output of gate is 0, the signs are identical. If it is 1, the signs are different. Okay, so what if the output of the sign is identical? So if we think that I am using the exclusive OR between the two signs A and B, if my output gate is 0, the sign is identical. If it is 1, the sign will be different. So for an add operation, identical signs indicate that the magnitude be added. For add operations, identical signs detect that the magnitude be added. For a subtract operation, different signs detect that the magnitude be added. So okay, so the two the magnitudes are added with the micro operations, that is EA gives us to A plus B, where EA is the register, EA is the register. Here what we are saying, the magnitudes are added with the micro operations. EA is A plus B. So where EA is the register that combines the EA, register. EA is the register that combines the EA. The carry in E, E after addition constitute, or the carry in E after addition constitutes an overflow if it is equal to 1. The value of E is transferred into add overflow flip-flop AVF flip-flop AVF. Okay, so next in this we having two magnitudes. The two magnitudes are subtracted if signs are different. If two magnitudes are subtracted, if the signs are different for an addition, for add operation, or identical for subtract operation. So I am taking the two magnitudes are subtracted. Two magnitudes are subtracted if the signs are different for an add operation, or identical for the subtract operation. So the magnitudes are subtracted by adding A to the 2's complement B. So no overflow can occur. If the numbers are subtracted, so AVF is clear to 0. Okay, so 1 in E indicates that A greater than equal to B, and number in A is correct result. If this number is 0, the sign A must be made positive to avoid a negative 0. So 0 in E indicates that A less than B. For this A less than B. Okay, and if for this case it is necessary to take the 2's complement, the value in A, the value in A, the operations can be done with 1 micro operations, that is A's complement plus 1. Okay, so we assume here, that A register has circuits for micro operations, complement and increment. So 2's complement is obtained from these two micro operations. In other parts of flow chart, the sign of result is the same as the sign of A. So no change in A is required. So however, A greater less than B, the sign of result is complement of the original sign of A. So it is necessary to complement A to obtain the correct sign. Okay. In this we having the final result is found in the register A, and its sign in it's a sign. So the value of AV of provides an overflow indication. The final value of E is in immaterial. So we can here we have a block diagram of the hardware for implementing the addition and subtraction operation. It consists of register A and B and sign flip-flops as sign flip-flops A's and B's. Subtraction is done by adding A to the 2's complement of B. So the output carry is transferred to flip-flop E, where it can be checked to determine the relative magnitude of two numbers. Okay, so the add overflow, the add overflow flip-flop AFEF holds the overflow bit when A and B are added. So the A register provides other micro operations that may be needed when if the sequence of steps in the algorithm. So I have the diagram here. So in this this is the flow chart of add and subtraction operations. What we are saying, we having the subtract operation and add operations in this. So a subtract operation means A, I am taking the two magnitudes A and B, that is A is the minute in A and subtract and in B. If I talk about the add operations, A is the A magnitude is the adjoint in A and addend in B. Okay, so here I am providing, what we are saying, that here I am providing the exclusive OR operation, exclusive OR gate. So between the two magnitudes, okay, A's and B's, between I am providing the exclusive OR gate. So what they are saying, so I having the EA here. So in this EA, so in if the identical sign indicates that magnitude B added, for a subtract operation, different signs detect the magnitude B added. So in the magnitude of added, so what we are saying, if the exclusive OR, if I get negative 0, if I get the sign 0, so if the sign is 0, the value will be identical. Okay na? So if the sign, so what we are saying, that here exclusive OR it will carry the 0. If it is equals to 0, so it will be identical. Identical means equal. A equal, and AS is equal to BS. So if it is 1, if the sign is 1, it is not equal. Okay, not equal. I have seen this point. I have explained now only this point in this. Okay, so combines. So yes, not equals to B. So if it is equals to EA will be adds A plus B, where EA is the register here, and it combines the EA, and it carry E after the addition constitute overflow and equal to 1. Okay, so if the value of E transferred to add overflow flip-flop AVF. Okay, so the two magnitudes are subtracted. If sign is different, add operations are E. So what is your E here? Here E is the register. So after that, if it is a 0 sign, so A greater than, A less than B. Okay, what they are saying, that if E is 0, if E is in 0 indicates, so A less than B. Okay, the number A is correct result. A is the correct result. The number if it is if this numbers is 0, a sign A must be positive and avoid the negative 0. Okay, so if it is indicates 1, even it indicates A greater than equal to B. Okay, so the number A is the correct result. Okay, if correct result, sorry, here this is the point, correct result. If numbers 0, if numbers is 0, if this number is 0, if this number is 0, the sign A must be add, positive to avoid the negative 0. Okay, negative 0. If it is E indicates this 0, A less than B, for in this case it is necessary to take the 2's complement of the value A. So the operation can be done with one micro operations, that is A's complement plus 1, A's complement plus 1. So A register has circuit the micro operations and complements and increments here. So 2's complement sign A, it is necessary to complement here to obtain the correct sign. Okay, so the final result will be found in the register A and sign A's. Okay, sign A's. If AVF provides overflow indication, the final value is in normal. So it same as in this also, exclusive OR. If it is equal to 1, so whenever it equals, the two values are not equals. If it is 0, it equals to A is equals to B. So this is the register, and A is added to the combines with the E, and AVF is the E. Okay, so this is the working of this flow chart for add and subtraction operations. So next coming to multiplication. So multiplication algorithm. So what is mean by multiplication algorithm? So in this multiplication algorithm, so in this multiplication algorithm, in the beginning the multiplicand is in B and the multiplier is in Q. Okay, multiplicand is in B and multiplier in Q. So their corresponding signs are B's and Q's respectively. We compare the signs of both A and Q, both signs A and Q, and set to corresponding signs of the product sign. Since the double length product will be stored in the register A and Q. Okay, so the register A and A and E are cleared, and the sequence counter SC is said to be number of bits of multiplier. So in this we are having the A and E. A and E are the two registers are cleared, and the sequence counter, SC means sequence counter, so set a number of bits of the multiplier. Since here the operand must be stored in its within its sign, one bit of the word will be copied by the sign, and magnitude will be consists of n minus 1 bits. Okay, if it is 1, the multiplicand B is added to the present partial product A, otherwise 0. Okay, if it is 1, the multiplicand B is added to the present partial product, that is A, otherwise it will be 0. Okay, so the register EAQ is shifted to the right and form the new partial product. The sequence counter is decremented by 1. The sequence counter is decremented by 1 and its new value is checked. If it is not equal to 0, the process is repeated and a new partial product is formed. When S is equal to 0, it stops the process. So in this is the diagram of the multiplicand. In this we having, in this multiplicand we having a m and m, n minus 1, so on, m of 0, m0 here. So I am having the n bit adder here, and shift and add control logic, and we are adding some values in this n bit adder. So after that we are having the C here. In this C I am having the A n minus 1 to A of 0 and Q n minus 1 to Q of 0. So this is shift right. We are shifting the right. Okay. and after shifting the right, and it will be goes to the queue of n multiplier. Okay, so this is the multiplicand, and this multiplicand will be transferred to the n bit adder. So the n bit adder shifted to the a n minus 1. Okay, this is the registers, and this will be shifted to the right, and it will be moved to the multiplier, and the multiplier will be passes to the shift and add control logic. After the value is added in the n bit adder, and it will be passes to the C. Okay, so this is the working of this multiplication. Okay, and this is the table having the C here and A Q M. Okay, and initial values. So I am providing C is 0 here. So this is the diagram. So in this I am providing the C is 0. So this is the A. Okay, so in the A value I am providing the 4 zeros, 0 0 0 0. So after that in Q, so this is the diagram. So in this Q I am providing the value that is 1 1 0 1. Okay, in M is the multiplicand, Q is the multiplier. Okay, so in M multiplicand I am providing 1 0 1 1. Okay, so these are the initial values. So next I am giving C is equal to 0. So my value will be changes. Okay, 1 at A value I am providing the 1 0 1 1. So in Q the same value will be represented 1 1 0 1. Okay, and again M is the 1 0 1 1. Okay, so this is the addition, it is the first. So after shifting the values means how it will be shifted. So 0 1 0 1 0 1, after that 1 1 0. So this like I shifted. So here see 1 1 0 1, I am in the M value. So at Q value I having the 0 1 1 1 and 1 0 1 0. Okay, so this is the shifting of bits. So in the second cycle, so this is the first cycle. In the second cycle, so my value will be 0 0 1 0. Okay, so and in the Q I having 4 ones, 1 1 1 1. Okay, so 1 0 1 1. Okay, so this is the second cycle. That's like we having the 4 cycles. In the 4 cycles we are shifting the values. Okay, so this is the multiply operations, multiplicand of in B and multiplier in Q. So I am providing the A's. A's is the QS exclusive or BS. So here Q's QS exclusive BS. Okay, so A, if A is 0 and E is 0, E is 0, and SCN sequence counter is n minus 1. So whenever I am providing the conditions to equals to 0 or 1, QS will be shift EQA SC minus 1, and equals to 1 it will be A plus B. Okay, so if it is equals to 0, the SC will be sequence counter. It is a sequence counter. When it is not equal to 0, it will be moves again, the repetition will be occurred. If it is equals to 0, the products in is in AQ is ended. Okay, if it is equal to 1, if it is QS is equal to 1, EA implies A plus B operations will be performed, and it will be moved to the it will be shifted to the EQA register, and sequence counter will be occurred SC minus 1, and this is the another condition now I have discussed. Okay, this is called the flow chart for multiply operations. So next coming to the Booth's algorithm. So this is the Booth's algorithm. So in this Booth's algorithm gives the procedure for multiplying the binary integers in the signs 2's complement representation. It operates on fact that strings of zeros in the multiplier require no addition but just shifting and string of ones in the multiplier from bit weight 2k to weight 2m can be treated as 2k plus 1 minus 2m. So this is the Booth's algorithm. In this we are having the hardware for Booth's algorithm. So sign bits are not separated from the rest of the register. Sign bits are not separated from the rest of registers. So rename the registers AB and Q, as AC. So A, B and Q I am providing the I am renaming for the registers A, B and Q as AC, BR, QR. Okay. So if you see this diagram, so BR is the register here and AC also register, QR also registers. Okay. So in this sign bits are not separated from the rest of the registers. So Qn, here we are having the Qn to Qn n minus 1. Okay. Qn designates the least significant bit of the multiplier in a register QR, and flip-flop Qn plus 1, Q here n plus 1 this one. So flip-flop Qn plus 1 is appended to QR to facilitate a double bit inspection of the multiplier. Okay. So this is the sequence counter, and we are here complementary and parallel adder. Okay. So this is the hardware for Booth algorithm. Okay. Next, this is the another flow chart. This is we are starting from here. So if A is 0, Q minus 1 is 0. So M multiplicand, Q multiplicand, count C. So this is my data. So how I am performing the operation. So Q0, Q minus 1. Okay. Q0 and Q minus 1. So all the multiplication schemes, Booth algorithm requires examining the multiplier bits and shifting the partial product. Okay. Shifting the partial product. So the multiplicand may be added to the partial product, subtracted from the partial, or left unchanged according to the following rules. Okay. And in this multiplicand is subtracted from the partial product. Multiplicand is multiplicand. So which is multiplicand here? M. Multiplicand, which is multiplicand is which one is M. Okay. So here multiplicand is subtracted from partial product. A is the partial product. I am subtracting the M multiplicand in the partial product. Upon encountering the first least significant one in a string of ones in the multiplier. So the multiplicand is added to the partial product upon encountering the first 0 in the string of zeros in the multiplier. Okay. And multiplier, the partial product does not change when the multiplier bit is identical to the previous multiplier bit. Okay. And the algorithm works for positive the algorithm works for positive or negative multipliers in a 2's complement and representation. This is because negative multiplier ends with the string. A multiplier ends with the string of ones, and the last operation will be subtracted in the appropriate weight. Okay. So the two bits of the multiplier in Qn and Qn plus 1 are inspected. If two bits are equal to 10, 10, it means the first one in a string of 1 has been encountered. This requires the subtracted and multiplicand from the partial product in AC. Okay. So if the two bits are equal to 0, 1, if two bits equal to 0, 1, it means that the first 0 in a string of ones has been encountered. First is 0 in the string of 0 has been encountered. This requires the addition of multiplicand to the partial product in AC. So when two bits are equal, the partial product does not change. Okay. So this is called the algorithm of the Booth's algorithm. Okay. Next, coming to divisions algorithm. So what is mean by division algorithm? divisions of two fixed point binary numbers in sign magnitude. Representation is performed with paper and pencil by a process of successive compare, shift and subtract operations. So binary division is much simpler than decimal division because here the coefficient digits are either 0 or 1, and there is no need to estimate how many times the dividend or partial remainder fits into the divisor. So this is the example of the division algorithm. So what they said, division of two fixed point binary number is signed magnitude. Representation is performed with processing the successive compare, shift and subtract operations. So in this binary division, we are taking simpler than decimal division because here the coefficient digits are either 0 or 1. Okay, and this is the example, this is the divisor, this is the dividend. Okay, so this is the division, this is the coefficient, this is the remainder. Okay, so this is the example problem of this division algorithm. So the divisor is compared with the 5 most significant bits. So this is the 5 most significant bits. The divisor is compared. The divisor, this is the divisor. So is compared with 5 most significant bits. So 1, 2, 3, 4, 5. 5 most significant bits. Okay, of the dividend. Significant bits of the dividend. Since the 5-bit number is smaller than B, we again repeat the same process. Now 6-bit number is greater than B. 6-bit number is greater than B. So we place A1. We place A1 for the coefficient bit. Okay, for coefficient bit. So we are providing 1 here. Coefficient bit in the 6th position. Above the dividend, and now we shift the divisor, once to the right and subtract it from the dividend. So the difference is known as partial remainder, because the division could have stopped here to obtain the coefficient of 1. So and remainder equals to partial product. In this so whatever the remainder is there, that remainder should be 1. If it is 0, the remainder will be 0. The result will be successfully ended here. So in this when comparing the remainder with the divisor, it continues the process. If the partial remainder is greater than or equal to the divisor, the coefficient bit is equal to 1, and the divisor is then shifted right and subtracted. From the partial remainder. If the partial remainder is smaller than the divisor, the coefficient bit is 0 and no subtraction is needed. The divisor is shifted once to the right in any case. So the result gives both coefficient and a remainder. So this is called the divisor algorithm. Next, coming to hardware implementation for sign magnitude data. So this topic will be discussed in the next class. So this is the topics hardware implementation for sign magnitude data, and this is the algorithm and floating point arithmetic operations, and so these are the explanation of these floating point operations, and this is the diagram, and this everything will be discussed in the next video class. Thank you.